Good morning, everybody, and welcome. My name is Tom O'Brien. I am the Executive Director of the Center for International Trade and Transportation at Cal State Long Beach, and we are a partner in both the MetTrans Transportation Consortium. Take note of our new name, please, we want it to reflect the kind of work that we do. And for MetTrans, I serve as the Deputy Director under Dr. Ioannou. We are also a member of the Pacific Southwest Region University Transportation Center, which is another consortium that features 8 universities in the Pacific Southwest region, 5 of which have doctoral programs. And over these 2 days of the Emerging Scholars Research Symposium, we've had representatives from all 5 of those doctoral serving institutions. Yesterday, we heard about transportation and the environment, transportation and natural disasters, and we had a keynote from Dr. Susan Handy from the National Center for Sustainable Transportation, and also PSR, who was our keynote speaker. Today's sessions are going to focus on 2 additional topics. One is from the world of freight, which is what my day job is, and I will be moderating that discussion. We've got 3 really interesting presentations that I'll introduce to you once we launch that. And that will take us to 10:45. At 10:45, we'll take a break, reconvene at 11 for a session on mobility. And that one is going to be moderated by, as you can see on your screen, Dr. Anastasia Lukatos-Sideris from the UCLA Luskin School of Public Affairs. And then please make sure to stay for the 12 p.m. keynote from Senator Fran Pavley, who is the Environmental Policy Director for the USC Schwarzenegger Institute. Fran has about 14 years of experience in the California Assembly and State Senate, was instrumental in the development of some key environmental policies, including AB 32 and SB 32, which I assume that she'll be talking about. But this is a really good opportunity to hear from somebody who can talk about the development of policy related to climate, and also their impact, in areas that are the subject of discussion today, such as freight and mobility. So I think it will be interesting for you all to hear from her, so please stay tuned. Before I introduce our first speaker, I just wanted to say something to the students. I was a Ph.D. student at USC in the Price School before it was the Price School. And at the time, we had something similar that was hosted by, at that time, UCTC out of Berkeley, which was a Ph.D. presentation roundtable that was hosted on our campus. So I was in your position, and one of the people who spoke at that session from Berkeley, Peter Hall, became a friend and colleague, and we actually just submitted a paper to this year's TRB. So my lesson to you is this is an opportunity in many ways, not only to develop your presentation skills, but also to identify like-minded researchers. And I'm thrilled that we did not do the coordinated research symposium for a number of years, and I'm thrilled that we're back, and this is now the 3rd year. So I'm going to transition into our first session, which is related to freight routing and modeling. And you're going to be hearing different approaches to solving vexing problems to the freight sector in Southern California related to congestion and environmental quality. So what I'm going to ask is for Pengfei to put up his slides. And while he does that, I'll let you know that our first speaker is Pengfei Chen, who is working on his Ph.D. degree with the Center of Advanced Transportation Technologies at USC. His research interests lie in the intersection of complex systems modeling and complicated routing algorithms. And he's going to be talking about a really interesting topic, which is related to what happens when you inject electric trucks into a regional network that is largely based on diesel operations. And he's going to look at some possible solutions to both understanding and solving that challenge. So turn it over to Pengfei Chen.
Thank you, Dr. Tom O'Brien. So hello, everybody. I'm Pengfei Chen from University of Southern California, and I'm honored to be here in the symposium to share the progress made on mixed freight routing and load balancing we do with co-simulation optimization approach from Center for Advanced Transportation Technologies, USC, under the supervision of Professor Ioannou. So let us start with some statistics. So worldwide container trade is growing 9.5% annually. Freight transportation is a significant contributor of NOx, CO2, PM 2.5, and other pollutants. For example, 26% of the CO2 emissions are caused by heavy-duty vehicles, congestions. And congestion in urban area causes 4.3 billion more hours delayed and 2.9 billion more gallons of fuel consumed annually. A non-negligible non-negligible amount of congestion in urban area can be alleviated by proper coordination between different trucking companies. So with the development in the intelligent transportation system, such as sensors, navigation technologies, and advances in zero-emission trucks made in recent years, we think the freight transportation system can be a benefit from the incorporation of the electric trucks, advanced simulation software, and optimization techniques. So the objectives of our project are, first, we'll develop a traffic flow simulation model with the ability to reconfigure itself in real time and account for the dynamics of different classes of trucks to predict travel times and flows. Second, we integrate the real-time traffic simulator with vehicle routing optimizations and evaluate the feasibility of the schemes for fast real-time routing decisions. And third, with the simulator and the optimizer, we develop a centrally coordinated routing system with mixed freight vehicles. And at the end, we examine the impact of the mixed freight coordination in aspects of total cost and emissions. So here I show the general form of the optimization model. Here you can see the solution denoted as capital X, means the number of certain type of trucks taking a route from a region to a destination at a certain departure time K. The route is in the form of a node sequence indicating the node passed through to the end of the route. In the objective function, we use capital S to denote the average service cost per container or per truck, since here we assume that one truck can only load one container. The average service cost includes the energy cost as well as the travel time cost. And the constraints in the following shown explicitly show that the constraints is from two ideas, which is one, the total demand for each pair of OD origin destination need to be fulfilled, and two, set certain type of trucks at each node is constrained by its availability. And with the formulation constructed, let us move to the methodology we propose. We first input the information of origin destination demands, mixed freight distribution, road networks, etc., into the optimum load balancing sector. In this sector, we build a service network that is in charge of optimization, which includes minimum cost route researching, updating, load balancing. The minimum cost of route searching and load balancing need traffic status updates, which is provided by the traffic simulator after it. As for the traffic simulator, it simulates the solution from the optimal load balancing sector. And it simulates the solution, which is the assignment flow from the optimization sector, as well as the background traffic data from other traffic data sources, and predicts the traffic status and feed it back to the optimal load balancing sector. And the loop along the optimization and the simulation ends if the solution converges. Then we take the final solution as the assignment for the mixed freight fleets. Next, let me explain some sectors of it in detail. So since the model needs the characteristics of different types of freight inputs under realistic working status, we start to gather some surveying projects using diesel and electric trucks. And the projects includes the Port of Los Angeles interior electric drayage, Foothill bus, Frito-Lay delivery truck, Smith Newton truck study, and Navistar East truck study, and studies from California Air Resource Board. And we then here's a table that summarizes the characteristics in these projects. For example, the electric trucks of Class 8 in the Port of LA, its maximum speed is 60 miles per hour on level ground, and it will reach 30 miles per hour in 21 seconds. It's settled. And here are some dynamic characteristics of the top popular diesel freight vehicles we gathered. As you can see here, the acceleration characteristics are not provided in these projects. So to find out, we have another sources. So here we can see that from another literature, the acceleration performance of diesel freight trucks. The test includes 71 diesel trucks. The table shows that in the first 6 meter, they accelerate at 0.65 meter per second square. From 6 meter to 15 meter, they accelerate at 0.6 meter per second square, etc. And here we also gather the fuel economy of freights used in these references. For instance, Class 8 electric trucks used in the Port of LA covers 10.8 miles with 1 diesel gallon equivalent energy. But however, the aforementioned literatures consider the fuel consumption they consider the average fuel consumption, and average fuel consumption only reflects the limited information because working conditions of vehicles may change and the fuel economy will vary a lot. Also, since we tend to implement a very detailed traffic simulator for this project, which will provide us with plenty of traffic network information, we then propose to use analytical energy consumption models of diesel and electric freight vehicles with the help of our simulator. The analytical energy model is then implemented and tested with 5 drive cycles suggested by National Renewable Energy Laboratory. The units units we used is a kilowatt per hour. Next, let us move to the next sector, which is the load balancing sector. And first, we need to configure the service network. As we can see here, the road network shown on the left is the area around the Long Beach and Los Angeles port terminal area. There are around 30,000 nodes and 75,000 links in this road network, which need to be considered in this problem. It is computationally inefficient to directly apply optimization methods on it. So other than that, the dynamics of the traffic networks are complicated. So the way we choose is we introduce a higher level service network using traffic status aggregated from the traffic simulator for the optimization purpose. and use the traffic simulator to take care of the dynamics of the traffic network. And as we can see on the right, we present the corresponding service network maps for the road network on the left. The basic idea of the mapping is to choose different important nodes from the road network and connect them accordingly. So other than the original destination nodes, such as node of the importance, such as the intersections of the freeways and the major arterial ways are considered in the service network. Here are the algorithms we propose. With the road network from the simulator and service network in the optimizer configured, the algorithm run as the following. Step 1, we do the initialization for some predetermined parameters, and in the step 2, we check if the solution converges in terms of improvements on the total cost, and then in step 3, we use the concept of marginal cost, which will be used to appropriately adjust the assignment iteration by iteration in order to avoid overlapping routes that will lead to higher travel times. About marginal cost, we will discuss it in the following page. In step 4, which we update the marginal costs, and we check whether there is a minimum marginal cost route. If there is, we add it into the route collection, which means that if a new minimum marginal cost route is found, it will be considered in the following iterations in the algorithm. And in step 5, here we take care of the availability issue of mixed truck at each node, since we include the electro trucks into in problem, and it is very crucial for the electro trucks. The availability issues for the electro trucks is crucial to the problem. And in step 6, this step we update the assignment for the next iteration. So about the marginal cost, it basically represents the change in the total cost if one unit of demand or container is changed in a certain path. Here, capital MCP denotes the marginal cost. TC means the total cost. Y denotes the volume of type, some certain type of truck on some path of the service segment with departure time. Okay. And eta is denoted as the time value, and T is the travel time. C is the energy cost, and since the derivative of the T over Y and C over Y is included complex inclusion of traffic system status and need much more space to explain, we leave them encapsulated. And how we can use these marginal costs in the algorithm. So we can use it to give us a descent direction. So with the marginal cost updated for each link in the network, we can check if there is a new minimum cost path exists for each pair of OD. By solving the following linear programming that takes care of the availability issue of trucks at each node, we can obtain an augmented route flow vector X hat, which can be used to generate a descent direction by minus the assignments from the previous iteration, which is X, capital X. And another use of the marginal cost is it can help us to choose the step size. So the idea is if the marginal cost of all the paths for a specific OD are close to each other and the volume on them unfeasible, then the assignment for this pair of OD is balanced. We use the standard deviation, and if the standard deviation is close, and the standard deviation is regarded as a criteria of the balance, if we are balancing or not. We then evaluate the emissions and fuel consumptions of output assignment results with MOVES model. The emissions estimated include hypercarbon, CO, PM 2.5, and XO, CO2. And then we do some experiments for our proposed methodology. The road network covers the Los Angeles Long Beach Terminal Port area from the south side to I-105 freeway in the north side. The total number of demand is 1,715. And the distribution of the mixed freight is that we assume the total number of mixed freight at each origin node to be the same as the container need to be transported at node. We then gradually increase the percentage of the electric trucks from 0 to 100% at a 10% step, and we also test we test the methodology under the background traffic of light traffic, medium traffic, and heavy traffic. And the total cost we show here are depicted in two ways: with charging time or without charging time. The total cost without charging, including charging cost, decreases as the number of electric vehicles increases, while it tends to increase if charging time included. And as expected, the emission goes down drastically as the number of electric vehicles increases. Similar patterns are revealed when the system tested under medium and heavy traffic conditions. So here are our conclusion. The total cost without including charging time decreases as the number of electric trucks increases. And the total cost that also includes the charging cost tends to increase in general with the increased number of electric trucks in the fleet. The assumption made is that the charging cost includes the labor cost of a driver waiting for the vehicle to be charged. So if charging cost is down off duty, this cost can be reduced considerably. Thank you.
Thank you, Pengfei. We have our first question, and what I'm going to ask is, Alicia, if you could take yourself off mic and ask your question to Pengfei.
Thank you. Please reveal the fundamental approach's signification to the transportation demand management as a methodical tool on the design stage of the eliminating criteria for the technological thresholds at the transportation infrastructure development level. Thank you.
So first of all, the significance of the project or the contribution of the project is that other than the classical logistic problems that assume the travel time, that assume the assignment from the optimization, the background traffic, the whole traffic transportation system will not be affected by the decisions of logistics. We assume that the background or the whole transportation system can be affected by the decisions of the logistics problems. And we included the dynamics of the transport, and we include the dynamics or the reaction of the whole transportation system to the decisions of the targeted problem, which is the truck assignment problem.
I have a question for you.
Yes.
Pengfei, I approach the question of freight and electric trucks from a policy perspective. And I have a two-part question for you. One is, what have you learned in your research about the market for battery electric trucks? And this is a question that I would likely ask any of the panelists. What do you think is the most valuable finding from your research for the trucking sector, for the industry itself? What do you think they would be most interested in about your research?
The truckers?
Yes, truckers themselves.
I would say that so for me, the future for me, so the truckings can be, or delivery of the truckings can be divided into short haul or long haul. And my next step of the research, I think, will be the trucking platoons, which can be used in the long haul, or it is already used in the Europe from the Volvo company. So they use trucking platoons, and I think some researchers about from Japan also research this problem. That is the trucking platoon. If we use trucking platoon, it will give us more safety, and the energy consumption will be reduced about 20, based on different size of the platoon, from 25% to 50 or 60% from some literatures. So I think that will be the next stage of my research and the future of the trucking. That is for the long haul. And for the short haul, I think, as I said, the number of the short haul trucks will affect the background traffic or the whole transportation system around, especially around terminal area. Considering the number of the trucks entering and exiting the terminal area. So I think the classical logistic problem that, considering especially the with high volume of trucks, I think they need to, or we need to consider its impact on the whole traffic transportation system, and which we need to balance these trucks into different routes based on the that is the spatial load balancing. Or if we can move further, we can consider that the trucks can be we also need to consider the schedule of the trucks, which is load balancing in the temporal dimension. So in the end, it will be spatial temporal load balancing kind of thing.
This, by the way, is an area that PSR has really taken a leadership role and is understanding the various aspects of deployment of battery electric trucks into the local freight sector. That includes the kind of work that Pengfei is doing, studies from an economics perspective that looks at drivers' propensity to shift from diesel to battery electric. Sue Dexter, who I think is on the session here today, has also done work on the market and the willingness of drivers to adopt battery electric technology and other alternative fuels, including hybrid fuel cell. Our next speaker continues the theme of responses to the challenges of freight operations, complex freight operations in Southern California, with a discussion of container movement modeling with double container trucks under stochastic demand. And this is another possible response to the need to reduce both traffic congestion and air pollution in communities where trucks operate. If I understand correctly, I took a little preview of Siyuan's presentation. There's also an interest in the role that transloading plays in Southern California freight operations, and this is an interesting aspect of the Southern California freight sector, and I'm sure we'll all learn from Siyuan's presentation. Siyuan Yao is a doctoral student majoring in industrial and systems engineering at USC. He works under the direction of Professor Maged Dessouky, who is a good person to be learning from, I have learned. And he is conducting work in not only the topic you're going to be hearing about today, but also other freight-related challenges, including empty container repositioning. He uses tools such as co-simulation and mixed integer programming for transportation systems. So with that, let me turn it over to Siyuan Yao.
Thank you, Doctor. So hi, everyone. My name is Siyuan Yao, and I'm a third-year PhD student at ESC, working with Professor Maged Dessouky. The research that I'm going to present today is stochastic demand container movement modeling with double container trucks. So first, let's talk about some background. So in 2018, global containerized trade reached the volume of 152 million 20-foot equivalent units. So here are two pictures. The left one shows the annual container statistics in the Port of Los Angeles, and the right one shows the imbalance in the inbound and outbound containers. So taking the Port of Los Angeles and Long Beach as an example, the I-110, I-710, and I-405, three main transportation corridors in Southern California, are congested because of the container movements in the San Pedro Bay Area. So in 20 years, the container movements in the area will be doubled with a very conservative estimation of 3% annual growth. As Pengfei mentioned, for now, there's like about 10% annual growth. So if the container movements are not handled carefully, the traffic congestion and air pollution problems would be further exacerbated in these areas. So to handle the large number of containers arriving and leaving at the port, warehouses are built in the port area to support the port operations. So there are three types of warehouses, including importers, which handle import containers, and exporters, which handle export containers, and depots, which can temporarily store containers. So the current container movement in the port area is shown in the top graph. So in this situation, it's quite inefficient because many of the container movements are transporting empty containers going back and forth between the port and these warehouses. So in the statistics, about 30% of the containers were empty containers. Therefore, a lot of researchers have been studying how to move these empty containers efficiently. In the literature, the problem is studied as empty container repositioning problem. Here are two empty container reuse strategies have been studied in the previous literature. One is called street exchange, which allows an empty container to go from an importer to exporter directly instead of returning to the port. So the second one is called depot direct, which introduced depots into the container movement network, thus allowing temporary storage of these containers. Besides preceding research conducted by Professor Dessouky and Dr. Carvajal introduced the double container trucks into the empty container repositioning problem. The model is called Double Container Assignment Model, DCAM, which studied daily operations for moving containers. The model showed the benefits of using double container trucks. First, it can reduce the total number of trips, and it can reduce the total number of trucks in the network. It can also increase the possible routes between all the locations. So from a managerial perspective, it can reduce the administrative cost as well, because you have less trucks to manage. So a single container truck can only carry one loaded container or one empty container, but a double container truck can carry two empty containers or two loaded containers, or one loaded and one empty container. So in this case, the possible routes between all the locations increases. However, the model has its limitation. The model assumes a truck must drop off both its containers before allowing for another pickup. So in my research, we have overcome this assumption. So I will introduce that later on. So here are more literature talking about the empty container repositioning problem. There are deterministic models and stochastic models. There are also studies focusing on policies, and some researchers study the problem together with traveling salesperson problem. So, okay, let's talk about the optimization model. So the first model that I'm going to introduce is double container flexible pickup and drop-off model, the DCFM model. So the main difference between the DCFM and DCAM is given in the model name, the flexibility. So which means the pickup and drop-off requirements is relaxed in the new model, the DCFM model. Therefore, a double container truck can pick up any loads when capacity permits. The main decision variables in the model is the number of trucks in state R leaving from location I to J with a departure time T. So, and the truck states are defined as the following picture. So in our model, there are 3 types of containers, including import container, empty container, and export container. Therefore, a double container truck can have 10 possible states. So we use triplets to represent the truck states, where the first, second, and third element be the number of empty export and import containers respectively. So for example, in the first case, a truck is not carrying any containers. We denote that as triple zeros. And if a truck is carrying 1 empty container and 1 import container, we denote the truck state as 101. So after defining main decision variables, so let me introduce the general model information. So in general, we built a mixed integer programming model to solve the empty container repositioning problem. In our model, we have 4 types of locations, including importers, exporters, depots, and ports. So importers can transload import containers to empty containers. Exporters can load empty containers and turn them into export containers. And depots can store containers temporarily without any transloading capabilities. There are 3 types of containers in our model, as I mentioned. They are empty containers, export containers, and import containers. So the demand and supply information at each type of location are given in the table. So for example, importers will receive import containers and turn them into empty containers. Also, in our model, we assume that each location has deterministic demand, and all the demand has to be strictly satisfied by the end of the day. And the time is discretized in our model, and the distance matrix and the travel time are predetermined. And all the import containers are available to be picked up at the port at the beginning of the day. Here is our DCFM model. It has the following constraints. The first are the capacity constraints, which basically means the total number of containers at each location cannot exceed the location capacity. Then by using our decision variables, we can capture the container flows between these locations. Therefore, we will have the container conservation constraints at each location. Also, we are using double container trucks to carry these containers. So we have vehicle conservation constraints for each location. And for importers, exporters, and the port, they all have its demand. Therefore, we have the demand constraints for these locations. And in the end, we have the transloading constraints for importers and exporters to describe the transloading process in these locations. And the objective function is to minimize the total truck miles and the number of trucks for one-day operation. And after propose the model, we feel like in practice, we cannot only focus one specific day because the problem is not meant to be solved in a vacuum. Therefore, we proposed a stochastic double container flexible pickup and drop-off model, which is called SDCFM. The S represents the stochasticity. So we introduced the future stochastic demand into the model. And by considering the second day demand, trucks can make strategic movements for tomorrow's demand in the first day. And in this model, we developed a rolling horizon-based solving framework. Basically, we solve a 2-day problem iteratively and only implement the first-day solution. So this is our solving framework. So we assume the first-day demand is deterministic, and second-day demand follows a Markov chain in which each state has some probability distributions. We assume the transitional probability and probability density function of demands can be obtained by from the historical data, and we also assume the port has S different scenarios, each with probability delta S of occurring. Also, since we are looking at a 2-day problem, we have to consider the connection between the container allocation at the end of the day, at the end of the first day, and the container allocation at the beginning of the second day. So we assume that import containers stay at an importer will be unloaded to empty containers overnight. And similarly, for the empty containers stay at the exporter will be loaded to export containers. So not like the first day demand has to be strictly satisfied. We allow second day demand to remain unmet, but with penalty cost. So the second day constraints are very similar to the previous constraints. We still have the capacity constraint, the container conservation constraint, and the transloading process constraints. But for the second day constraint, demand constraints, we relax the constraints by applying some penalty on the unmet demand. So after that, we have to build a bridge between 2 days, and the connection is the second day initial state constraints. In SDCFM, our objective function is to minimize the total truck miles for 2 days and minimize the total number of trucks we used for the first day, because we only implement the first day solution. And here is a brief summary of all the models. So the DCAM model is the published model, show the benefits of employing double container trucks into the empty container repositioning problem. But it has a pickup and drop-off requirement. And the DCFM model is the new model which relaxed the pickup and drop-off requirements. But both of these two models only focus on 1-day problem. So on top of that, we introduce SDCFM and incorporate the future demand into the DCFM model and figure out and solve the problem by the rolling horizon-based approach. So let's talk about the experimental analysis. So we ran experiments on San Pedro Bay Area, and the daily horizon is 12 hours, which with time discretized into 1 hour length. And the capacity for all the transloading locations are 20 units of containers. And in this case, DCFM performs about 15% better than the DCAM model in the base case. And therefore, we also conducted the sensitivity analysis on the DCAM and DCFM as well. So we run several tests, and in average, the DCFM model performs about 14% better than the previous model. So after showing the benefits of relaxing pickup requirements, we also investigated the benefits of incorporating future demand. Since both DCFM and SDCFM are mixed integer programming models, it may take a long time to find the optimal solution. Therefore, we limited the computational time to 20 minutes of an i9 CPU. And we compared both of DCFM and SDCFM against a solution, knowing perfect information for the 10 days, which means, so in the SDCFM, we have a certain transitional probability for the port state from 1 day to another. But for the perfect information model, we assume all these states are given. Therefore, we built a very large integer programming model for the perfect information case. But since the model is too large, we solve the LP relaxation of the perfect information model. And the numbers in the tables are ratios of model solution versus the LP relaxation. So both DCFM and SDCFM are solved collectively for 10 days, and each experiment was run for 5 trials. So we show that relaxing the pickup and drop-off requirement, we can reduce about 15% of the daily truck miles. And in addition, incorporating future demand can further reduce the system cost by about 8%. So if we can predict the second day demand more accurately, the model can perform even better. And future research can investigate the scalability of the model and account for unexpected events that might occur during the study horizon. And that's my presentation.
Thank you, Siyuan. We have some time for actually a good amount of time for some Q&A. I will remind, I'd like to have the people who have joined us since we started to post in the chat and let us know where you come from. We're happy to have you. We have a couple of questions. One is actually, Siyuan, a question from Sue Dexter that I also had, which says that, you rarely see double trailers in LA. Do you know why? Have you thought about how to modify this for three trailers, which 13 states allow, but not California?
So for this question, so the reason we do this project is because in this area, they want to see the benefits of employ double container trucks. Although for now, because the traditional trucks are all single container trucks, but if we want to employ that, we have to invest a lot in updating these trucks, right? So the purpose of the published research, which is the DCAM model, is to investigate how much we can gain from employing the double container trucks. And the research results shows it can reduce about 30% of the cost, which is a lot. And therefore, we have our following researches. So the reason for, there's another reason for double container trucks is not widely used in LA is because the size of the truck is very large, which may impact the road traffic congestion even more. And also the turning ratio of the double container trailers is different from the single container trailer. So that is why it is not widely used in LA area. And hope that answers the question.
Thank you. What kind of quantitative indicators of innovativeness of the territory establish the effectiveness for urban planning system in the field of the transportation based on the functional regularities of innovative development of industrial and civil construction at the present time? Thank you.
Yeah, let's see. There may be a couple of questions in there. I don't know if you might want to break them up into sort of a primary and a secondary. That might help.
Maybe innovative development of the territory by the industrial and civil construction laws at the present time at the territory.
So I think for the civil construction perspective, maybe, for example, when we design the road, we have to consider the turning ratio of the multi-trailers, because the turning ratio is definitely different from the previous vehicle, and it will be much larger, like the radius of the road will increase, for example. And maybe there's also regulations about when, which road or which lane should these multi-trailer trucks can run on the road. That's also need to be specified, because when these type of trucks changing their lanes, it might be more dangerous than the current trucks.
Siyuan, I have another question. What your presentation helps, I think, the audience understand is the complex nature of cargo moves in Southern California. I've done some work in this area too, focused on the chassis, right? So that's the trailer that you put the container on. And I know that there's a number of repositionings that occur to move the chassis, not just the container. And I'm just curious whether the question of chassis has come up in your modeling, and what, because that might add actually VMT to the equation.
So excuse me, doctor. Could you please remind me what chassis is?
Sure. So for the intermodal containers, and the container rests on a chassis, and it can be detached from the chassis. So in addition to moving chassis, or in addition to moving containers, you also are moving the trailers as well. So I was just curious whether your model would allow for that type of container. Now I recognize that the intermodal container may not be the focus of your research, but I'm just curious whether the model would accommodate different types of movements of cargo within the Southern California basin.
Oh, so you are basically talking about the trailer part.
Correct.
So for example, so in my model, I was modeling the container movement, but there is another type of trailer that can link to the truck and then just haul away, right?
Correct.
So in that case, we can consider the chassis as the part of the container, right? So in that case, we can just use the model, but just use a different name, right?
So it might be interesting, and I know that Maged has also done some work in this area. But one of the challenges with container movements in Southern California is that the chassis is owned and operated separately. And in some cases, the truck driver has to move the chassis between the port and another facility, which adds additional moves, right, to the process, which is why I'm thinking it could possibly increase VMT. So I just throwing it out there as something that might be interesting for future research.
Yeah, that's actually a very good suggestion. I will consider about that. Yeah, thank you. Thank you, doctor.
For the model to improve prediction accuracy, do you see any logical ways to involve the historical data and to establish a process for future data updates?
So basically, we are assuming that port have different scenarios. For example, if there is a ship leaving at the port, so they might have the port might have a higher demand for export containers or empty containers, and if there's a ship arriving at the port, then they will generate a lot of import demand, right? So in that case, we can investigate the ship scheduling data from the port, and to study how the port scenarios will transform. Like, as I mentioned in the previous slides, so we will have these transitional probabilities. And these transitional probabilities, we can get it from studying the historical data. So like, if there are 2 consecutive days of ship leaving, then it is very likely for the next day to have a ship arrival. Hope that answers your question, Zoe.
Okay, seeing none, I want to thank Siyuan Yao for a very interesting presentation. I'd like to start with the third presentation, our third of three this morning, focusing on different aspects of freight operations in Southern California. Our third presentation is going to come from Aristotelis Angelos Papadopoulos, who is working toward his Ph.D. degree at USC with the Center for Advanced Transportation Technologies. He works with his advisor, Dr. Petros Ioannou. His research interests are in the fields of machine learning, deep learning, optimization, and game theory. And he's also interested in applications in financial markets, transportation, and social media. So all very interesting mix. Today, Aristotelis is going to talk about another challenge in the Southern California freight sector and the freight sector in general. And that is the impact of lack of coordination among a very distributed truck driver network, and whether there are possible solutions to allow for better coordination with advantageous impacts on the system. So Aristotelis, take it away.
Thank you very much for the introduction, Dr. O'Brien. Hello, everyone. My name is Aristotelis Angelos Papadopoulos. I'm a PhD student at the Department of Electrical and Computer Engineering, working under the supervision of Professor Petros Ioannou. And today I'm going to present a work which is part of my PhD thesis, entitled Personalized Pareto Improving Pricing and Routing Schemes for Near Optimum Freight Routing, which is actually an alternative approach to congestion pricing. So regarding the outline of the presentation, first I'm going to talk about the motivation behind our work. Then I'm going to formulate the problem. Then I'm going to talk about the well-known user equilibrium and system optimum problems. And then I'm going to talk about the first approach that we proposed in this work, which is the optimum pricing scheme. Then we are going to move forward to the approximately optimum pricing scheme, which let us scale our experiments in larger networks, and then some simulation results and conclusions and future work. So it is known that the transportation sector comprises almost 9% of the nation's economic activity as measured by the gross domestic product here in the US and about 5% in Europe. Traffic congestion is one of the major problems, especially in urban areas. And on the US highway, it annually costs the trucking industry more than $60 billion in operating expenses and almost 1 billion hours of lost productivity. Additionally, the trucks are responsible for 20% of the GHG emissions coming from transportation. And the fact that freight traffic can be flexible with respect to schedules and routes give us the opportunity to design some schemes that could make their operation much more efficient. So in general, it is well known that the users of the network act independently in order to minimize their own individual costs. And when we are talking about cost, we could say that this would correspond to travel time through, for example, the use of GPS technologies. However, it is well known, in theory, that user optimality, which is implied by the use of GPS technologies, which minimize the individual travel time, does not imply system optimality. So when everybody is minimizing his or her own individual travel time, the solution that we get in the network as a system is not optimum. This inefficiency between a user equilibrium solution where everybody is minimizing his or her own individual travel time and the system optimum solution has been addressed in the literature with a term like price of anarchy. Ideally, we would like this term to take values close to 1, but in realistic transportation network, it has been observed by real data that this value takes the price of anarchy takes values much larger than 1. Which means that there is enough space for us to optimize the operation of the network. So additionally, here in this work, we are gonna consider the user heterogeneity in the value of time of the truck drivers, meaning that we will assume that we can have that different drivers have a different value of time. Some drivers might have a value of time of, let's say, $50 per hour, some others $30 per hour, some others $100 per hour. In the previous work, it has been shown that the value of time-based pricing schemes can increase the feasibility of implementation of pricing schemes in general, since they can take into account the vulnerable user groups. Previous research effort, they have actually claimed that the value of time can be considered unobservable, or in some other cases, they make assumptions that the value of time might follow like some specific probability distributions, which makes this assumption kind of unrealistic. So the research question that we would like to answer, like in our work, is if there exists a way to learn the value of time of each driver by clustering the driver into distinct classes of value of time, and subsequently use this information to build value of time-based pricing schemes. So in order to do that, we will make like some mathematical assumptions which are common in the literature. First of all, we are going to consider like a symmetric information model. And since we want to apply some pricing and routing schemes into the truck drivers of the network, we assume that the symmetric information means that every truck driver has the same amount of information about the traffic condition. We consider that we have multiple classes of users. As I said before, it can be $20 per hour, $40 per hour, $60 per hour. And we assume that we have a stochastic demand, while on the other hand, we have a coordinator in the network which can know the exact realization of the demand. So the setting here says that the truck drivers might know the exact number of passenger vehicles in the network. They might know the probability distribution of the demand, but they might not know the exact realization of the demand. This is like a realistic assumption in the sense that whenever someone is using like a GPS technology, this GPS technology is making some traffic flow predictions which include uncertainty. And this demand uncertainty that we use in our model is trying actually to model implicitly the uncertainty that we have like in the traffic flow prediction models. So as I said before, we are trying to design pricing and routing schemes that are going to be applied in the truck drivers. And so we have an overall coordinator in the network who is going to ask the truck drivers to declare their design origin-destination pair, from which origin to which destination they would like to travel, and additionally pick their value of time from a set of n available options. And his or her like objective will be to minimize an overall social cost function. We will later define the social cost function, what social cost function means. So yes, so first I would like to talk about the user equilibrium problem. The user equilibrium problem, I'm not going to stick to the math that much. So the user equilibrium problem is actually a mathematical model that describes the condition of the network when every user is trying to minimize his or her own individual travel cost, which in our case, we are talking about travel time. So this is the mathematical formulation of the user equilibrium model. And as I said before, a user equilibrium model is user optimal, but it's not system optimal. On the other hand, the system optimum model is trying to minimize here the objective function that you see like in this mathematical formulation is trying to minimize the expected total travel time of the trucks in the network, the expected total travel time of the passenger vehicles, and the expected total monetary cost of the truck drivers, which is actually a weighted combination of their travel time weighted by the value of time of the class they belong. So someone would say, okay, since user equilibrium implies user optimality, but user optimality does not imply system optimality, why don't we apply the system optimum problem in the network right away? That's like the first question that someone like could think of. But the thing is that the system optimum, in a system optimum solution, some drivers may benefit while some others may be harmed compared to the user equilibrium, which means that this could lead like to unfairness issues, and nobody would actually like to participate in if a system optimum solution would be applied like in the network. So the idea behind and the main motivation behind our work is how we can design routing and pricing schemes that could drive the network as close as possible to a system optimum solution, while at the same time guarantee that each individual user who is participating in our mechanism is going to be better off than the user equilibrium, which means it's going to be better off compared to the case where he or she is taking individual routing decisions by minimizing his or her in the individual travel time. So based on this motivation, as I said, we're trying to design a mechanism, and the main criteria that we want to satisfy, the first is the Pareto improvement, which means that we would like to make everyone better off compared to the user equilibrium. We also want to, since we are going to ask the drivers to pick their value of time from a set of n available options, we would like to satisfy some truthfulness property. This is the key property here, because when you ask someone to declare their value of time, everybody would like to declare a very high value of time so that he or she is going to be assigned in the fastest possible route. So having the truthfulness property here guaranteed is very important. Additionally, in order to achieve the truthfulness and the Pareto improvement property, we thought about applying a mechanism which is actually going to be a kind of exchange of payments, or let's say credits, between the drivers. So when we assign like a driver to a faster route, he or she is might have like to pay an amount of money or credits, while on the other hand, in the case where someone is accepting to follow like a slower route, he or she is going to receive a payment which could be like in the term of credits, in the form of credits. So since we have like this exchange of payments, we would like to design a mechanism which is going to be self-sustainable, and that's what we mean here by budget balanced on average. And of course, as I mentioned before, we also want like to drive the network as close as possible to the system optimum solution. So these are the main criteria that we want to satisfy by our design. So we have here two decision variables. The first decision variable is the decision variable alpha, how we are going to distribute the truck drivers into the network, how we are going to route the drivers. And the second decision variable is the pi, which is going to be the pricing scheme, the payment made or received, which could be in forms of credits, as I mentioned before, by the truck drivers. So here we formulate an optimization problem, which you don't have to stick to the math. The objective is a weighted combination of the expected total travel time of the truck drivers, the expected total travel time of the passenger vehicles, so that we do not disrupt the network by routing the truck drivers, and the expected total monetary cost of the truck drivers. And the constraints simply say, make everyone better off compared to the user equilibrium. The second constraint says, guarantees actually the truthfulness property, that everybody will have an incentive to truthfully declare his or her value of time. And the third constraint says that they will have a self-sustainable mechanism. So this problem, the optimization problem that I just showed to you, can solve our problem, but the main problem with that is that it cannot scale to very large network. And the question here is whether we can do faster than that. And the answer to this question is yes. So what we have here, we have a second optimization problem where we are saying that instead of calculating both decision variables through a single problem, we can calculate only the way, we can optimize only over the way we are going to distribute the drivers into the network. And we are going to design a pricing scheme, which is given by the first equation pi that you see here on the slide. And this equation says, the first term says that we should make everyone pay or receive a payment that will make his or her cost to be equal at his or her cost at the user equilibrium, i.e., in other words, like at the case where he or she would minimize his or her own individual cost. And then, after we bring everyone at that point, we calculate the total monetary benefits from the mechanism. And from these total monetary benefits, each class will receive an amount which is proportional to the value of time that this class has. And when we take this amount, we uniformly actually distribute this amount among the truck drivers of this class of value of time. So here we mathematically proved that by solving for the decision variable alpha only through an optimization problem and then calculating the payment through a single algebraic equation, we can guarantee all of the mechanism design criteria. In other words, drive the network as close as possible to the system optimum solution, make everyone better off compared to the user equilibrium, guarantee the truthfulness properties about the value of time, and having a self-sustainable mechanism. And here we are gonna actually compare our work with some previous research efforts, which include the congestion pricing scheme. Many of you might already be familiar with it. So congestion pricing says that we are going to try to decentralize, let's say, the user equilibrium model. And how we are going to achieve that? By applying fees, appropriate fees at each road segment of the network. The uniform revenue refunding scheme says that if we have a coordinator, the coordinator will collect these fees and will equally distribute the collected fees back to the truck drivers. So this is a class anonymous pricing scheme, meaning that it does not consider the value of time of the drivers. And here we are designing value of time based pricing schemes. In the simulation experiments, we will show that by considering value of time based pricing schemes, we can achieve much more efficient solutions for the transportation network. So in our simulation experiments, we run our simulations in this benchmark network, the benchmark shear-fall network. It has 24 nodes and 76 links. We assume that there are passenger vehicles at each road segment of the network. When we route the truck drivers, we only consider the 10 least congested routes per OD pair in order to make the decision from which route like each truck driver should follow. And we also consider that we also assume that we have two classes of value of time. The first one is $200 per hour. The second one is $50 per hour. And the truck drivers are asked to pick their value of time, to pick like one of the two classes. Some additional details that I don't have to go through at this point. And what I would like to mention here, I would like you to take a look at the bottom right figure, where we actually plot the total objective value of our optimization problem. So this total objective value is, as I said, a weighted combination of the expected total travel time of the trucks, the expected total monetary cost of the truck drivers, and the expected total travel time of the passenger vehicles. As you can see here, the optimum pricing scheme, OPS, and the approximately optimum pricing scheme, AOPS, which are like the proposed approaches, can approach the system optimum solution, which is shown in blue, while at the same time they can achieve a much lower cost compared to the congestion pricing with uniform revenue refunding scheme, which has been previously proposed in the literature and is denoted by the red line, and a much better solution than the user equilibrium solution, which is the solution in the network in the case where every driver is trying to minimize his or her own individual travel cost. Another point that I would like to make here is the following, because I mentioned that when I first introduced the optimum pricing scheme, OPS, I said that it cannot scale to very large networks, and this is what I want to show here. Here in the first table, we increase the number of origin-destination pairs for the trucks. We start from 4, then to 8, to 12, to 16, and to 20. When we are talking about the congestion pricing with uniform revenue refunding scheme, we see that when we reach 16 origin-destination pairs for the trucks, the problem becomes computationally intractable. On the other hand, for the optimum pricing scheme that I said that it might not scale that much in large transportation network, it is shown here that when we reach the 20 origin destination pairs, again, it becomes computationally tractable. However, if you take a look at table 2 and the approximately optimum pricing scheme, we see that when the number of origin destination pairs is 20, then the approximately optimal pricing scheme can be solved in 446 seconds in our simulations, which is a pretty fast solution, given the fact that all of these algorithms that we are talking about are like actually planning algorithms. So to conclude, our main motivation was that the network usually follows a user equilibrium solution, which implies user optimality. However, user optimality does not imply system optimality. On the other hand, we cannot apply a system optimum solution in the network because some drivers may benefit while some others may be harmed compared to the user equilibrium. And that's why we wanted to design some pricing and routing schemes. Compared to all the previous research efforts, which assumed that the value of time of the drivers is generally unobservable, or they were making assumptions about the distribution that the value of time of the drivers might follow, here we were able to come up with a design that allows us to ask the truck drivers to pick their value of time from a set of n available options and guarantee the truthfulness property, providing, in other words, we provide incentives to the drivers to truthfully declare their value of time. And we use this information to design value of time-based pricing schemes, which has been shown to be really beneficial in previous research efforts. So in future work, we would like to extend the current approach and apply it to passenger vehicles. We would also like to, instead of having a route-based pricing scheme, which means that we calculate a different pricing, a different payment for each route, we would like to design a different payment for each link, which would help us to scale our experiments further. We would also like to extend the current approach so that it can be applied in real time. As I said, the current approach is mostly a planning approach. And at this point, we are also working towards another direction. So it is well known in the literature that except travel time, various other factors can influence the individual routing decisions of a driver. And based on that, we are trying to extend the current approach to take into account all of the other factors that might affect routing decision, which could be, for example, distance, which could be familiarity with specific routes or the number of freeway interchanges, let's say, etc. Thank you very much for your attention, and I'm open for any questions that you might have.
Yeah, thanks, Aristoteles. Very interesting. We have one posted, again from Alessia, and I think if I understand it, she's asking about how do you control for some of the more dynamic aspects of the system, and she's provided some examples there, and maybe that's what you were getting to at the end of your presentation about some of the other variables.
So, as I said, this is like mostly a planning approach. And when we are talking about a user equilibrium solution or system optimum solutions, we are talking about the network being in an equilibrium solution. When we are talking like about transportation networks in reality, we can we often have, most of the times actually, we have disruptions in the network, which does not allow the network to reach the equilibrium solution. So in this current work, we haven't taken into account the dynamic properties of the transportation network, if this is what the question asks about. But I would like to mention that in general, the literature can be divided into two main parts. The first part is talking about networks being in an equilibrium, and in the second part they are talking about the dynamic aspect of the networks. Usually researchers start from solutions that are talking about equilibrium conditions in the network, where someone can prove some mathematical concepts that can form the foundation of some future, let's say, methods that could be applied in a realistic transportation network, and then take into account the dynamic aspects. So this is a very important question that you asked here, and this is something that we plan to take into account into our future research efforts.
Thanks.
Thank you for, oh, sorry. Thank you
go
for
ahead.
your presentation and answer. Thank you. Sorry.
No, thank you, Alicia. We have another question asking about the social costs. So the social cost includes the weighted travel time of the drivers. Have you considered any other costs, or do you think adding other types of costs might improve the model's outputs?
Okay, so the current cost is a weighted combination of the travel time of the truck drivers and the monetary cost of the truck drivers, which is a weighted travel time for the trucks. Additionally, because we are only applying our method like to trucks, we are also taking into account the travel time of the passenger vehicles, because we don't want to really disrupt the network by our operation. This is what I mentioned, like that is a part of our future plans, is to include more costs into the network. And actually here, there we are going to define the concept of a utility, which the utility is going to include, it's going to be a weighted cost of different factors. Let's say, for example, how much one driver values like the distance of a route in his or her routing decision, while at the same time we are trying to minimize the overall travel time of the network. Of course, other costs like taking into account the environmental impact of our methods, of course, they should be taken into account, and this is something that could also improve our models and make them much more feasible and closer to implementation for realistic transportation networks. So this is something that we need to take into account into our future research efforts.
Thank you.
Thank you. That's just to clarify, you mentioned social code. That's why it popped up in my head, that other than exactly my travel time or monetary cost, are you considering other environmental impacts or not? That's why I asked this question.
Mm-hmm. Yes,
Thank
I
you.
understand. Yes.
Yeah.
And I'll take the moderator's prerogative to ask the last question, or at least a thought. One of the things that impacts travel time that we've observed is the availability and location of truck parking. And this will become, I think, more of an issue as the transition to battery electric occurs, and where charging stations are located and how they relate to hours of service regulations. It's a very, I love the topic, because the value of time for truck drivers is dependent upon so many factors, and you're getting to the heart of some key issues that I think they're important. So I don't know to what extent you've looked at truck parking, and I will share with you there has been some use of crowdsourcing technology to gather truck driver information on available offsite truck parking locations. Phoenix's regional transportation plan included data from a crowdsourcing study. So given your other interests in I guess artificial or machine learning and deep learning, there might be some interest for you there in that other work, and I'm happy to share you what I know about it offline.
Yes, of course, I would like you to share like this work with me, and I would like to mention here that a colleague of mine, we are working at in the same lab under the supervision of Professor Petros Ioannou, is working and into the parking availability constraints, and he's taking into account all of the possible, all of the regulations that currently exist regarding when truck drivers, how many hours like consecutive hours of work a truck driver should drive, and take into account whether there is going to be like a parking availability, and where he or she should stop while doing like his or her like scheduling trips. So this is a very important problem. This is like an active area of research, and this is like a conversation that I also have like with one of my colleagues like in the lab. So yeah, I would be really glad to share like this work with me.
Great. Well, we're at the end of our time. I want to thank and congratulate all of these researchers for sharing their work with us. One piece of, if I might, just suggestion, you're doing really all important work and helping translate your findings, particularly for people who are interested in the policy end of things or the institutional questions surrounding your topic. A slide looking at the impact of your work and the transferability to practitioner industry is always a really nice way, I think, to end presentations and remind people of how your work could be applied elsewhere. And because you're all doing really important stuff, broadening your audience is something that I would encourage. So I want to thank you, and I want to thank everybody for listening and taking part. And we have now a 15-minute break. And at 11 o'clock, we'll be turning it over to Dr. Lukiris to lead the discussion on mobility.